I'm Xinyi, and my topic is an agent-based simulation of household heating adoption, which is integrating Bayesian belief updating. So first, let me briefly introduce the background. We have an urgent global need to reduce carbon emissions, and which has intensified the focus on transition to sustainable energy solutions. And residential heating accounts for approximately 10% of national emissions in countries like the Netherlands, where the predominant use of natural gas for home heating is a key factor. So we need a more detailed model to simulate a group of homeowners' decision-making process of heating. And let me introduce agent-based models. An agent is an autonomous individual element with properties and actions in a computer simulation. And agent-based modeling is the idea that the world itself can best be modeled by using agents and environments and descriptions of agent and agent environment interactions. The concept of agent-based modeling is one of the best ways to describe the complex systems that we see around us. And agent-based models are now often used in energy-related investments or adoptions modeling to examine producer and consumer behavior. This table compares three heating system investment options: heat pumps, district heating, and no investment, which means keep original equipment in the house heating. And the heat pump has the highest initial cost in setting in this model, but offers near zero carbon emissions, making it high energy efficient. District heating has a moderate initial cost and medium running cost, which with emissions varying based on the energy source. The no investment option means residents make no change and so has no initial cost, but is the least efficient and most environmentally damaging due to high emissions and energy consumption. So this table 2 details the parameters and agent profiles using the model. Household characteristics like income and environmental concern play crucial roles in determining investment capabilities and preference for sustainable choice. Thermal need is calculated based on the number of occupants and their health status, while insulation quality affects the preserved efficiency of heating systems. Energy usage patterns and investment costs for different heating options significantly impact the net present value, which is NPV, and long-term benefits perceived by households. By simulating these parameters, the model captures the diverse decision-making process and preference of households. Now we layer on different decision-making styles. People think differently, so they will also make decisions differently. We include 4 different types of agents. The first is rational, which is most evidence-driven. They are rational agents. And the second type is satisfying. We'll set good enough thresholds for them. And the third one is social, and they will have higher impact from neighbors' influence. And the last one is conservative, who are risk-averse. And these styles don't change the economics. They only change when the decision's trigger is put. And the simulation framework is as presented. The simulation begins with 1,000 households, and each household is uniquely defined by a set of attributes that were introduced before. The core of the simulation runs through 15 steps, representing a span of 15 years. And each cycle or each step is a crucial period where households making decisions. And agents update their decisions based on various factors, including the recent choice made by their neighbors. And besides, households annually reassess and update their intentions and financial estimations, leading to potential changes in decision making. So now let's look at the details of this figure. Let me expand. An annual decision loop is household follows. So first, they will update their beliefs about heat pumps, district heating, and original gas based on new information from their own experience or their belief, which are presented in the blue flames. And next, those beliefs feed the theory of planned behavior, which is our decision-making behavioral submodel, and giving each technology a utility score, which is in the green framework. And then a style-specific rule translates this score into a yes or no final decision. And then the household either switches their technology choice or stays unchanged, then moves into the next loop until it reaches 15 years. Let's go further into the Bayesian belief updating. And each household carries a beta distribution for performance, cost effectiveness, and the reliability of every technology. When they or a neighbor have a good outcome, the success parameter, alpha, increases, and the bad outcome raises beta. Updates are mathematically clean and beliefs gradually become narrow, so meaning the household grows more certain. Conservative agents, for example, they will learn slowly, and social agents learn fast. So from the very first year, households are already diverging in how confident they feel. Success pushes the curve right and failure pushes it left. The table illustrates the mechanism involved within a single belief updating period. And those evolving beliefs feed the theory of planned behavior, which is our decision-making rule. CIB says that the attitude, subject norm, and perceived behavioral control jointly drive intentions. For hitting adoption, that means how good I think this tech is and how many of my peers use it, and whether I feel I can actually install it. Utility equals the weighted sum of these elements. Attitudes comes from concerns and beta beliefs, expected performance, cost effectiveness, and reliability. And the second term, the subject norm, is the share of neighbors who have already adopted. Perceived control captures hard constraints, for example, income, savings, or building limitations in the system or capacity level. We draw the three weights from empirical ranges, so every household weighs these factors differently. And every household checks the utility for both techniques. Whether that the number is good enough depends on its style. So here are the results. Two figures on the left are the adoption curves across 1,000 household and 100 stochastic Monte Carlo runs. District heating climbs quickly because it's cheaper upfront, and heat bumps starts lower but accelerate faster as belief certainty grows. By year 15, fewer than 1 in 5 households remain on original gas boilers. For the figure on the right, this histogram shows the technology finally. On average, district heating holds about 41% and heat pumps about 40%. And here are the adoption and success figures by style. The two on the top are the breaking results done by style. Rational and satisfying households each see adoption rates above 40% and success, defined as positive net present value plus reliable performance above 90%. Social households adopt even more, but their success dips slightly, reflecting some peer pressure things. Conservative adopt the least and succeed only about 60% of the time, which also reflects that waiting too long means rebase, expire, and the learning is lost. And the two figures on the downside are the belief certainty evolution. This violin plot tracks how belief certainty tightens over time, and district heating beliefs converge faster and tighter because the technology is mature and network performance is predictable. Heat pumps believe narrow more slowly but still steadily. As variant collapse, perceive risk falls, and this the psychological tipping point triggering late-stage adoption. In other words, certainty, not just cost, drives the second wave. Our results highlight the diversity in decision styles, stretches the transition timeline, but prevents locking. Late adopters still have a safe pace once certainty rises. A portfolio approach that keeps both clean options attractive is more resilient than betting on a single winner. For a policy angle, it still needs its own nudge. Rational and satisfying household trust hard numbers, so publish performance dashboards or keep subsidies predictable. Social households follow visible peers, so from neighbors, pilots, or spotlight early adopters. Conservative households fear downside risk, so we can offer long-term warranties or shared savings contracts to blunt certainty. But we also have some limitations. The model simplifies reality, and real spatial networks could move cascade thresholds. Policy instruments are fixed here, but reward subsidies evolve. We also assume unlimited capacity. Installer bottlenecks or dislocating pipe work could slow adoption. To fill these gaps, we would use more empirical survey data, testing agents on real social networks plus dynamic incentives, and extending to collective decision making at the neighborhood or even larger scale, and adding voting and deliberation mechanisms. So here are the future work. That's all, thanks.